my name is Marcos Basso, and I will present a work entitled Complete Complementarity Relations for Multipartite Pure States, which in certain sense is the continuation of the previous work that I presented here. So I will give the motivation, an example, and what means to complete a complementarity relation. So in the last talk, I said that the complementarity principle was just recently uh, quantified in terms of inequality between predictability and visibility, where the predictability measures the particle aspect of the system and the visibility measures the uh, wave aspect of the system. But uh, this type of complementarity relation expressed through an inequality has some problems. For instance, as pointed out by Kian, this complementarity inequality does not really capture a balance exchange between P and V, because the inequality permits that V decreases due to the interaction of the system with its environment. This is called the coherence process. And for instance, the decoherence process can explain how the classical world emerges from the quantum realm, because the system interacts with its environment and loses its coherence. So V can decrease, and the inequality still will be satisfied, even though the predictability does not increase. So the inequality also permits that the decrease of P and V together, and also allows the extreme case where P and V is equal to zero. So we don't get any complementarity information about the system, even though we have a quantum system in hands. So Kian expressed this as such a quantum can be nothing. So you can see that something is missing for equations of the type 1. And as mentioned, for instance, we can consider a Mach-Zehnder interferometer and a photon or a one-half particle in such interferometer, and the state of the system after the beam splitter 1 is given by the equation 2, where A is just the probability of the quantum being transmitted. And in figure B, I plotted the predictability and coherence and as a function of A. But it's interesting to see here that the sum of the two is always maximal. The inequality always saturates in one half. And this is due to, this is because the state of the system is pure. Or it means that you can express the state of the system by a vector in a Hilbert space. However, this is not the most realistic way to represent the state of the system in interferometer, because the system interacts with its own environment. So a more realistic way is given by equation 3, where W represents the probability of the system is in state psi, while 1 minus W represents the probability of the state of the system is 1/2 of the identity, which represents a completely incoherent state. Such a state can be obtained by the action of a quantum channel, and quantum channels are used to model the interaction between the system of interest and the environment, in such a way that we don't care about the structure of the environment, if it's a heat bath or something like that.
So we can see that as W tends to 0, the coherence tends to 0 too, as well as the predictability, which is expressed in figure C and D. Although both remain complementary between each other, both tends to 0 as W tends to 0. So you don't get any information about complementarity. So as mentioned, one way to fix that is consider the correlations with the rest of the system or with the environment. And you can consider this by, how can I say, by consider the purification theorem, which states that it's always possible to find a pure state in a large Hilbert space such that our system is part of it, in the sense that you have a vector in a Hilbert space, and when you trace out the environment or the other part of the system that we don't care, we get the state of our system, which is expressed by rho A equals the trace the partial trace over B of the pure state. So, for instance, if you consider the maximal entangled state given by equation 4, when we discard or disregard the system B, it gives rise to the case for W equals 0. So you can see that we get no information about the system because the system is entangled with another system. So complementarity relation means that we add to equation 5 a measure of correlation that turns the inequality into equality, which is expressed by equation 6. So, for instance, a possible purification, because the purification process is not unique, for a state 3 that I given before, a possible purification is given by equation 7. So, for instance, now our system does need to be a quantum in a Mach-Zehnder interferometer. For instance, it can be a superconducting qubit in the IBM quantum computer, and the other system also can be another qubit. So, such that in figure F, we give a possible quantum circuit that implements such a state 7. So when you trace the other system, in this case, which is another qubit that we are not interested in, we recover the state given by equation 3. So it's just to emphasize that the other system can be a system that we have control of it or not, which in this case is the environment. So by consider the linear entropy as a measure of entanglement, you can see that we always saturate the complementarity relation, which is represented in the figure L. For any value of W, the sum of all three measures is always equal to 1/2. This idea was first noticed by Jacob and Bergot, where they consider the following 2-qubit state, which is a very particular one because it's just two systems with two levels. So they consider the predictability and visibility that I showed in the last presentation, and notice that when you take the concurrence measure, it's a measure of entanglement, which is related to the linear entropy, they notice that when one square each of them and sum the three, you get a number. In this case, it equals 1.
but in the last presentation, I showed that we derive several complementarity relations just by exploring the properties of the density matrix. And one of these measures, which is based on the Hilbert-Schmidt distance, in particular for qubits, our measure relate to those used by Jacob and Bergot by expression 9. In this sense, our expression is a generalization because it's for any d-dimensional system. So it suggests to us a possible generalization of equation A. So in the work that we published in the Journal of Physics A, we have the idea to try to derive equation 8, not just sum all of them and get a number in an ad hoc manner in this sense. So by considering that the hypothesis that it is always possible to find a purification for our system, and it is because it's just a mathematical theorem, and by exploring the purity of the whole system, because since the whole system is pure, it is represented by a vector in a Hilbert space, and this is the maximum knowledge that nature can give it to us. By exploring the purity, we find the complete complementarity relation given by equation 10, which generalizes equation 8, because is valid for any d-dimensional system and for any subsystem or any parties. So that's it.
Thank you. Questions? Preguntas?